So we're going to talk mostly about the classes we write. And you're probably familiar with the pitch, giant pitch metaphor from one of the herb stocks. There's all sorts of classes we usually write. Either utility, wrappers, function objects, all sorts of type hierarchies and polymorphic behaving types, containers, and of course, value classes, your plain old structs without any funny pointers inside. But some are more special than others. And what I'm going to try to explain is some of the characteristics of these types of classes and some of the unexpected behaviors that can arise from using them in weird ways. So I did talk about this topic a while back, 5 years ago actually, and it started some real good conversation back then, and this year I've been asked to revisit the topic, and that's why I'm doing this. So I'm going to start with this funny quote from Titus. Good types are all alike. Every poorly designed type is poorly defined in its own way. And it, of course, it alludes to the famous quote from Tolstoy. So why regular types? Why are we talking about this? So we shall see that regular types naturally appear as necessary foundational blocks in programming, and I'm going to try to take you with me on an investigation to see how they appear in the standard library, in specification, in requirements, and even in modern C++ in concepts and similar ideas. But even before C++ 20 concepts, we've seen these things in all sorts of guidelines, including the core CPP guidelines. We have C11 make concrete types regular. Regular types, this is quoting from the guideline. Regular types are easier to understand and reason about than types that are not regular. The C++ built-in types are regular, so are the standard library classes, such as string, vector, map, and so on. And concrete classes without assignment and equality can be defined, but they should be rare. And we have required template arguments to be at least semi-regular for similar reasons, including comprehension. So we have guidelines, we have conference talks, we have books. I'm going to mention one or two. And they talk about these concepts. And it all goes back to a fairly old paper by now. It's 25 years old. And it's the Alexander Stepanov paper from '98, Fundamentals of Generic Programming, where it talks about STL and it designs its design principles. And so my talk is not just about regular types. It goes and investigates values, primarily, objects, concepts. We're going to focus on ordering relations, requirements, equality. Equality is going to be a big part of this course. Whole part semantics for objects, of course, object lifetimes, and I already mentioned some of the guidelines. And it spans multiple C++ versions, because we have things coming in the library that make use of these concepts. So I do recommend, by the way, the slides are going to be peppered throughout with links and references to videos and articles. So when you get the slides after this, if you're inclined to investigate some of these things further, just follow the links. I do recommend that you watch this two-part series of talks by Titus Winters on modern C++ API design. Especially part 2, and where it discussed type families and combination of type properties in good type designs, and of course designing overload sets and other things. So good all around. But let's start with the beginning. Anyone seen this series of lectures by Alexander Stepanov? I see just 2 hands. Okay. So 4 algorithmic journeys, if you Google for it, it's actually 3. They cut it short. So these are the 3 tracks. It's fairly long. So I do warn you, if you're not really into this thing, it's very long. There is a sort of condensed Reader's Digest version on the internet in written form, if you want something like that. So if you don't have the patience to follow 32 hours of video content, and trust me, you cannot watch it on 1.5x on YouTube, I do recommend the book format. So the book format for the lecture series is this one, From Mathematics to Generic Programming. And it sort of goes through 4,000 years of mathematics, more or less, following from Egyptian multiplication and following basically a core algorithm like GCD in multiple incarnations, and how investigations in its nature and structure gave yield to new fields in mathematics and new ways of reasoning and structuring mathematical concepts. And up to sort of modern times, where we have incarnations of this kind of work in modern cryptology. Before we get started, let's just, we have to nail down some common vocabulary, because some of these terms are sort of overloaded and can be confusing. So I'm going to use terminology from elements of programming. So a datum is a finite sequence of zeros and ones and can represent anything. A value type is a correspondence between a species and a set of datums. A value is a datum together with its interpretation function. So an integer as 32-bit 2's complement, big endian, let's say, that's a value. And mind you, a value cannot change. We're talking here about the abstract concept of the value. Let's say 5. 5 is a value. It cannot change. Some laws in correspondence to equality. If a value is uniquely represented, equality implies representational equality. Sort of makes sense. And if a value type is not ambiguous, representation equality implies equality. So the other way around. But this ambiguous thing needs to be settled a bit more. And an object, and I don't mean here like OOP object. Object is a representation of a concrete entity as a value in computer memory. So its address and length, so where it lives in memory. And an object has a state that is the value of the domain of those value types. So an object has a state, which is a value. And of course, the state of the object can change. So what we store in memory at a particular location, if we store a 5, or if we later update it to a 10, that is something that can change. So the object, the location in memory. And the type is a set of values with the same interpretation function and operations on those values. We're sort of familiar with this concept. And the concept is a collection of similar types. And we're going to see what we mean by similar, what we expect from them. So all these terminologies and definitions come from elements of programming. It's I would say, one of the foundational books of our field. I know not everyone is familiar with it. Even fewer people have read it. From the people who read it, I always hear that it's impenetrable, or that they couldn't understand anything, or that it's too difficult, or too abstract, or too mathematical. And I get it. I get it. You sort of, it's good that if you try to read it in progression, and you sort of have to do multiple passes, and your understanding of the concepts within will be gradual when you come back to it and reread some of the things there. If you want like a gateway version to that, maybe you can start with this talk, which definitely very few people know about. So mathematics does matter. So it's greatest common measure, the last 2000 years. Very, very good gateway into EOP. So you can start that way. At least it worked for me. But you might say, okay, all this intro, all this mathematical bullshit, why should I care about that? I've been working for N years programming, and I didn't need any EOP or math stuff to help me. And the reason why things just work for you is because other people have thought about these hard concepts and encoded them either in the type system or in the libraries that you're using, so that it feels natural and intuitive to you. So it's not for free. It's not like, I don't care, it's somebody else's problem. Sure, it was somebody else's problem, and you're using the fruits of those struggles and rigorous design, sometimes rigorous. But I would argue that you should care, and I'm going to show why. So it's basically 4,000 years of mathematics leading to this paper, which I mentioned already. And the reason why you should care, even if you're using components that have been designed to make it easier for you, is that sometimes those components may fail you, and you may miss why. You might have surprising results, you might have weird behavior, and this is where your understanding of the world or that system or that design will start to fall apart, and you'll get lost on why that happened. We already got a hint of that in this morning's keynote by Kevlin. I'm going to mention it concretely later on. So generic programming depends on the composition of programs into components, which may be developed separately, combined arbitrarily, subject to well-defined interfaces. Okay, all nice and good. Sounds like the good stuff that all trainers preach. And among the interfaces of interest, the most pervasively and unconsciously used are the fundamental operations common to all C++ built-in types as extended to user-defined types. For example, copy constructors, assignment, and equality. Why am I quoting these parts of that paper? And it goes on. We must investigate the relations which must hold among these operations to preserve consistency with their semantics for built-in types and with the expectations of programmers. And this is why I'm quoting these parts, because the types that we design and the types that we're consuming, the functions that we're using, the algorithms from the standard library that we're consuming, make some assumptions. And if we're using them fulfilling those assumptions, or if we're using them sort of in contract on how they're supposed to use, and if the types we're designing or the types that we're extending or the types that we're using with, let's say, STL algorithms satisfy those assumptions, those requirements, then things will just work. And also, it's about uniformity and meeting the expectations. Like, even if we design something that works, but if it works very differently than other things that people are used to, then it breaks expectations and might be surprising, even if it does the right thing, if it even does the thing that you documented. So we strive for consistency with built-in types or the STL vocabulary types, intuition and expectation of programmers, and of course mathematical concepts that are established. You cannot reuse a concept like, I don't know, less than or plus to mean something radically different than what people expect from years of logic or mathematics. So we want a foundation powerful enough to support any sophisticated programming task, but simple and intuitive to reason about. Okay. You might see, okay, simplicity, that's overrated. Our problems are complex. We're building complicated things. We deal with C++. We're used to things being difficult. I sort of disagree with this. Yes, we're building very complex things, but they're all built out of very simple things, or at least they should be. So things that we can reason about, because it's very hard for us to reason about complex things, and especially relationships between many moving parts and complex systems are very, very, very difficult to reason about. So simplicity is a good goal, and the way to achieve that is build smaller things that we can understand and relations between those things that are unsurprising. And this is where regular types come in, at least one side of the story. And I would say, I would argue, an important part of the design. By the way, if you want a more modern take on fundamentals of generic programming by Stepanov, the '98 paper, if you want a newer, let's say, version of it, mentioning modern C++ and sort of a modern interpretation of that paper, I do recommend this one by Titus Winters. So it's a good synthesis, and it makes a case for regular types as well, of course, and was one of the inspirations for my talk. Okay, it mentions some of the new additions like string view and span. I'm going to mention those as well. So let's go back to the roots, STL and its design principles. Again, who has seen this presentation by Alexander Stepanov? This one is fairly well known, aside as opposed to the other one from SmartC. Friends? No? Nobody? Okay, then you should really watch this one. Okay, so I would say this is as best as I could describe it, is the manifesto of STL. So if you're a big fan of STL, if you're using it, if you want to understand how we got to this design and why some of these parts are designed in a certain way, maybe it feels weird to you, then this is the talk that you should watch. Okay, I'm going to try to extract the highlights from that almost 2-hour presentation. So fundamental principles of STL. Systematically identifying and organizing useful algorithms or data structures. Finding the most general representation of algorithms. Using whole part value semantics for data structures. And I'm going to revisit this item because it's very important. Using abstraction of addresses like iterators as interface between algorithms and data structures. This by now these are no longer surprising things, but back in 93, 94, these were like groundbreaking things. And usually algorithms are associated with a set of common properties of operations. For example, plus, multiplication, min, max. These are all associative operations. So that means you can reorder operands, and that means you can easily parallelize the operations built out of these kinds of operation chains. and we have concrete examples of these things like accumulate or transform reduce. So STL data structures, again, I'm taking you back to that Stepanov manifesto video that I recommended. STL data structures extend the semantics of C structures. No surprise there. This is the part that sort of trips people. Two objects should never intersect. And what I mean by that, they should model separate entities and separate lifetimes. And this is where we sometimes fail in our designs. And this is tied to the whole part semantics that I mentioned earlier. And when we copy a whole, we copy all its parts. When the whole is destroyed, all the parts are destroyed. Two things are equal when they have the same number of parts and their respective parts are recursively equal and so on. These all sound non-controversial things, I would believe. I don't think anyone will want to argue these points. But we sometimes fail miserably at modeling these things when we're designing stuff because of shortcuts or convenience. We might just add something in our type, or we might feel the need for some sort of connection that we need to establish between our types in the systems we design. So although we strive maybe for these things, we sometimes fail. I do recommend, how many of you are familiar with high-low programming language, or formerly known as VAL? Well, just one hand, okay. I'm not advocating that you go learn it or use it, but I would say that it's very instructive to read about its principles. And again, it has a nice website. There have been very nice articles about it and some presentations. I highly recommend this one by Dave Abrahams. I hope people are familiar with Dave Abrahams by now. So this talk covers at length some of the ideas of whole part semantics and how they relate to the design of high-low, and formerly known as VAL. So you can figure it out that if it has, or at least had VAL in its name, the language is very much about value semantics. So the talk will present some of the ideas of using pure value systems, some of the things, some of the learnings from Swift, what worked, what could have been done better, some of the limitations of producing an designing an industrial programming language that needs to integrate into existing ecosystem, and some of the limitations they had with Swift, and the path, the at least fresh start that high-low can get. Anyway, a very good, my opinion, very good exposition of building value systems and working with a value-oriented programming language. So again, that manifesto presentation by Stepanov mentions, introduces mainly programmers to generic programming principles, because back then it wasn't as popular as it is now. And it talks about abstraction penalty, which in early 90s was a really big thing. So some of the abstractions that STL introduced came with a runtime cost. So many of these went away, of course, as STL implementations got better and compilers got better at figuring things out. Of course, we have to deal with, so the Stepanov talks about some of these drawbacks, including implementation in the interface, early binding, horrible error messages up to this date, I would say, duck typing, some surprises when using these algorithms. For example, they might work with existing type that you're using in a system and fail to work when you change some of the behavior of that type, or if you're introducing a new type in the system, might surprise that it stops working. So, and the reason why these surprises appear is that we need to fully specify the requirements on algorithm types. And up until recently, these have been formulated in documentation form. But very few people actually bother to look up these things. And they're all documented in the language specification, and you can browse them on CPP reference, of course. And these named requirements were sort of the informal expectation of the STL, so that what they offer, the tools they offer you, actually work. And if you satisfy the expectation of each of those algorithms or data structures, because some of these apply to data structures as well, then they will just work. But if we fail to meet one of these requirements, surprises do appear. So named requirements are used in the normative text of the standard to define these expectations, and some of these, most of these, have been formalized using C++20 concepts. And they sort of look this way now. Just a few examples. These are not all of them. We can see them, a bunch of them that we're going to analyze today, like equality comparable, totally ordered, strict quick ordering. We see regular and semi-regular as well. So now they're fully formalized, and they appear in the actual implementations of STL, and they're actually checked by the compiler. So it's sort of more difficult to stray from the right path, I would say, but it still might be surprising when you get, sure, the diagnostic messages would be far better now, but you still need to understand the concepts and why you broke that requirement, because it will tell you that you don't satisfy that requirement, but you still have to figure out how does that relate to the thing, to whatever, my vocabulary type, my thing that I'm using with that algorithm. So formal specification of concepts makes possible to verify that template arguments satisfy expectations of the template during overload resolution and template specialization. Blah, 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 sounds very technical. What is important is that each concept is a predicate that is evaluated at compile time and becomes part of the interface of the template, where it's used as a constraint. So you might say, I usually don't design these things, I'm consuming them. And if I'm using it wrong, I'll get the diagnostic message, and sure, I'll deal with it. So sure, you can get by, but at some point when you expose either similar functionality yourself, and you might not be a library developer necessarily, but you might expose similar functionality in your application code. Again, you're going to run into the same problem, because people are going to expect the same kind of behavior from your code that they see from the standard library. So they would expect uniformity in behavior. And again, when you're designing your own types that you plug in, or if you're extending existing functionality, you'll have to deal with these concepts anyway. And I'm going to pick just one algorithm. Sort, because I assume it's one of the most popular ones in the STL. And we already see that we have a compare predicate there. So what are the requirements for a compare type that we have plugged into standard sort? Well, it's first of all, it needs to be a callable, which means we expect it to be a function object, and we expect it to be a predicate, which means it returns a Boolean value, and it sort of needs to be a binary predicate because we need to compare two things at a time. So intuitive, this is what we expect to be there. And we sort of expect a signature similar like this one, where we take two iterators and we have to decide which one goes first. But the big question here is what kind of ordering relationship is needed for the elements of the collection? So the stuff that we apply sort on. Let's say we're sorting a vector of t's. What do those t's have to be, or how do those t's need to behave so that it works? And I mentioned Kevlin's keynote this morning. Did you all remember do you all remember the set example with nans? That was a fun one, right? Just a refresher, and for the ones who are seeing this video on YouTube. So Kevlin showed a set of floating point numbers where we inserted some numbers, and at some point we inserted a nan, and then we asked about, okay, what's the size of the set? Yeah, and the other way around, we inserted a nan first, and then we inserted some numbers. What's the size of the set? Or we called the count function and to see how many nans do we have in the set, and so on. And all sorts of interesting answers that were certainly unexpected by the audience. And the reason why those were anecdotal, and you might say, I'm never going to insert nans in a set, or I'm never going to try to sort a vector that might contain a nan. Well, I'm not going to be so sure about that. So if you're dealing with floating point numbers, at some point, some nan value is going to sneak up on you. And you're going to end up with a nan value in a vector, and then you're going to sort it. Or the standard set example that Kevlin gave does the same thing. It tries to keep unique values, and it tries to achieve that using the less than operator that I'm going to talk about. So again, we're using a type. In Kevlin's example, it was a floating point number that doesn't behave like we expect it to. And it sort of breaks that contract just for some special values, like for nan, for example. So it breaks some fundamental properties that are expected, some fundamental requirements on that the algorithm imposes, or the data structure for standard set example imposes. The same kind of requirement is broken for both. And it works 99% of the time, but when it fails, it's going to be really ugly to see why. So I asked about compare. Is partial ordering enough? No. I have just a very simple example there of 2D points where we cannot decide an ordering relationship between all point combinations. For example, P2 and P3, we can state for certain in that example that P2 is less than P3, given the predicate that we defined. The predicate is the one under the picture. Whereas for P1 and P2, or P1 and P3, when we try to compare them using the same predicate, we cannot establish an ordering relationship. We say that it's undecided according to this predicate, and the formal way we state this is that the 2 points P1 and P2 are equivalent with regards to this predicate, because we cannot decide which one goes first. And it's not a defect of the point, it's the way we decided to compare them, the predicate that we're using. And that might be an external thing. For example, if we're providing the predicate as a lambda or a higher order function into the sort algorithm, or it might be a built-in, like if that structure implements a less than behavior. So it might come intrinsically from the type or be provided externally. So it turns out that partial ordering is not enough for sorting to work. We actually, what we're missing, and we can clearly see from that example where the points were equivalent, is that we're missing transitivity of equivalence. And this is what comes in to complete all the axioms required to form strict weak ordering. And yes, STL expects strict weak ordering. It's the very same thing that is broken for nans. And Kevlin actually explained that this stems from the fact that the result of comparing nans with other floating point numbers is defined, but it's not what you expect from strict weak ordering. So it's sort of, it's not a defect. So what comparing nan to another floating point number is defined by the IEEE standards to give as a predicate, as a Boolean result, is well defined, but it doesn't match up with the expectation of, or the requirement of the algorithm. So it breaks strict weak ordering. And equivalence, like I said, it just means that we cannot decide. So it's exactly the red segments in the picture. So we cannot decide which one goes first according to our comp predicate. So formally, yes, I warned you, it's good, it's math. So formally, these are the axioms that need to be satisfied by something to be strict weak ordering compliant. I think we're accustomed to seeing these in like 5th grade or 6th grade math. They're not exactly something new. So irreflexivity, antisymmetry, transitivity, and yes, we also need transitivity of equivalence. And it's sort of maybe a bit harder to follow because we have like a configurable comparator, like comp everywhere. But if you squint and you, instead of comp, you think about less than, then it's gonna make a lot more sense. But that's sort of a more strict concept than strict weak ordering. So yeah, strict weak ordering is actually formalized since C++20. So it's this concept. And its implementation is exactly what you expect with that table of axioms. So it just codifies the 4 properties required there. And like I said, it's far easier. I think this is what a 5th grader would recognize from a math class. So if we look at it with less than, so it's no longer a generic comparator, then this is the less than comparable concept, which is a different concept. It's a stronger requirement than strict weak ordering. All right, so going back to all those named requirements, we talked about less than. There's one more equality comparable that I want to cover, and this turns out to be one of the most important ones. And again, this should not be a surprise for a kid learning math in school. They might not like it, but this is what we're taught very early on about equality. And I would say meets the expectations. I don't think anyone sort of mistakes this or deliberately tries to break any of these assumptions when thinking about equality. And if we look at the formal definition using C++20 concepts, we can see how equality comparable concept is defined. It uses an intermediate thing, weak equality comparable with, so it has the same 2 types. that's just a more generic form. So we can see that it tests the exact same properties that we had in the table. So if we look at the table of the formal specification and the implementation of the concept, really this is the actual implementation in C++20. So this is what codifies those axioms. Now I want to stress a bit about the difference between equality and equivalence, because I would say this is where we sort of muddy the waters many times when we define stuff. So for types that define equality and less than comparable, STL makes a clear distinction between equality and equivalence, where equality is what we generally mean when we put that equal sign between stuff. And equivalence is that thing we've seen early on when we talked about partial ordering, when I showed the example with the three points in the picture there. So equivalence means when we cannot decide either way, when we cannot say that we say A less than B, no. B less than A, no. So then we say they're equivalent with regards to this predicate, to less than. Whereas equality means more, means identity in many cases. So equality is a special case of equivalence. And formally we say that equality is both an equivalence relations and a partial order. But that's just mathematical mumbo jumbo. So comp in total ordering, I told you that when we try to refine things and use less than instead of that generic comp we had in the axioms, then we're actually building something a bit stronger, which is a strict total ordering. This is what you come to expect from, for example, natural numbers. And the equivalence relations and its equivalence classes partition the elements of the set that are totally ordered. And if we look at the totally ordered concept as it's defined, we see that it exactly matches the mathematical definitions. Now, it's no longer a documentation story for STL at this point. Like, you should know these math concepts, or you should satisfy these requirements that are documented, but you should read that documentation. Now, they're actually codified now with actual C++ that the compilers can actually check and produce diagnostics about. And they very closely model what we see in those math tables. So STL assumes equality is always defined, or at least equivalence. So we can sometimes squint and say, okay, I'm building an equivalence relation here, and it works. So equivalence is more than enough for all STL algorithms and data structures to actually work. But we generally mean equality when we implement them. There are many cases where it makes total sense to implement equivalence, which is different than equality. Can anyone suggest an example of equivalence that is not equality? That we frequently deal with. For example, if we're trying to compare case insensitive some strings, yeah. So we say, okay, for the purpose of this operation, I'm doing a search. I'm searching a string. I don't care about it if it matches the case. I'm satisfied with the case insensitive match. So for my purposes in this workflow, in this operation, they're equivalent. But in reality, they're not equivalent, right? They're different representations of their different strings. Okay, so STL algorithms assume regular data structures. So that's why I'm making all the fuss about regular. That's why we're having this presentation. So STL was written with regularity as its basis. And we're going to see that even the standard broke that contract, that assumption. So what is regular? because I've been talking about ordering relations and requirements and concepts, but I didn't specify the regular concept. So we have to, again, this is the, I'm talking about EOP terminology here. So elements of programming, regular and semi-regular. So semi-regular, default constructible, move constructible, copy constructible, and so on, blah, blah, blah. All these properties. Yeah, we usually want all of them. Special mention for default constructible. One might make a case that asking for a type to be default constructible is not really a requirement for something to be regular, but it's usually what STL does for its types. Formally, this is how it's defined in C++20. Again, this is actual C++ code, no longer words from the standard. And regular just adds one more thing, equality comparable to that. So regular, it just means semi-regular plus equality. That's why I said equality is so important. And it's so difficult to define sometimes. And we're going to see that, and this is the, again, C++20 concepts implementation for the named requirement. But equality and defining equality is hard. It's very hard sometimes, depending on the thing we're trying to model. This is, again, a quote from the generics programming, fundamentals of generics programming paper. Two objects are equal if their corresponding parts are equally applied recursively, including remote parts, but not comparing their addresses, excluding inessential components and excluding components which identify related objects. A mouthful. What that means is that, and even Stepanov said that it's sort of, even this definition, although it looks complicated and complete, it's hand-wavy. So defining equality is really hard, and it's hard, especially when our types are not well structured. Remember when I referenced whole part semantics of objects and lifetimes and overlapping parts and so on, things that we should be careful when designing types. All those things complicate what equality means for those types, or even if we can define equality or equivalence for them. Special mention here for C++20 three-way comparison, which helps a lot. It brings consistency, it eliminates a lot of boilerplate, of course, but it adds complexity. So it removes complexity from your code, that stuff that you need to write, but it adds complexity in terms of the mental model and the stuff that you need to know now. So three-way comparison doesn't just return like bool, like true, false, or 0, -1, +1, or stuff that we've seen before. It deals in relation strength, and again, it ties back to the things that I mentioned earlier, those named requirements for how we order things. So it's all about the ordering relationship that we can establish over the T's that this spatial operator is synthesized for. So we need to be very explicit about the kind of ordering that we expect and use, and be very careful of weak equality. So yeah, it provides this handy syntactic sugar. It gives us some gateways to more efficient implementations, so we can separately specify equality and inequality for our types, and in combination with the synthesized spaceship operator. And this is to deal with more complex cases where a more optimal implementation of equality can be provided separately than the generic ordering relationship that's synthesized for the spaceship operator. If you want to see a lot of interesting examples of these kinds of optimization opportunities, what it means to default synthesize this operator for types, I do recommend that you read the original paper for this. The link is there. And if you're into videos content, this is by far the best presentation on the three-way comparison out there, in my opinion. Link is at the bottom. So sometimes we just want a value. Who has seen the Herb's keynote at this year's CPPCon? It's already online, by the way. Oh, that's a quarter of the room. Way better than I expected. Okay, so ignore the CPP front stuff and all the future-looking things. What I do care about is that Herb showed a way to formalize that something is of plain value. And of course, using the traditional point example. So the word value carries the meaning, and it's right there in the code. So it shows the clear intent, and there's no like a way around it, like documenting that this is a value. It codifies this. Anyway, I thought it was a nice touch. So again, sometimes we just want a value. But before we get too far with fancy CPP2 stuff, future-looking successor things, or if we're looking at C++ 23 or 26, and we have a few things from older C++ by now. For example, optional of t. So I'm not asking for a show of hands. I think everyone should be using optional by now. I hope you can. It's old enough. I hope everyone has access to stuff like optional. It has become a common vocabulary type. And why this matters is because optional extends t's ordering operations. So if your t defines any of those stuff, optional will extend these things. So as if they're t. So when you're comparing optional of stuff, if they will compare as if you compare your t's within. And of course, it saves you a lot of error checking and stuff. So it's good all around. Special mention here for optional of tref. This one you don't have access to unless you're using like a separate library implementation. I have my opinions on this. I think it's something that we need. It provides rebinding, shallow const, deep comparison, all good stuff. I'm optimistic. I still think we can get it. There are people actively pursuing this, so I'm still optimistic. But in the meantime, there are implementations out there. And I always say, learn from others. If you don't know what you're doing, look over the fence. So this is a Rust talk. I go into a lot of details of these kinds of things for examples with using continuations and the monadic extensions for optional. That's a separate presentation that I have. So another one, again, should be fairly accessible to everyone by now. I hope everyone is at least on C++ 17. Fingers crossed. I'm not going to do a poll because I'm scared of the answer. String view. Again, I'm not going to explain what it does. What's important is that it's a contiguous sequence of char-like objects, and it's a constant thing. So the underlying buffer is constant, right? That's the important bit. And string view succeeds admirably at being a drop-in replacement for a constraint ref. That's what it was designed for. It was designed to be a glue code, to be used at your interface boundaries, to be used as function arguments, as glue code, as your duck type for interconnecting all sorts of different string types you have in your system, and so on. So it's all good all around. But I think it was the first STL type that actually broke some assumptions for C++ programmers, because it was sort of weird. Because it looks like a value type. It looks like a string. Sometimes behaves like a constraint ref. when used with function arguments. So it looks like a value type. It can be cheaply copied around, so it sort of tricks you that it's a value, but it's actually not a value. And it's not actually a reference either. So it's sort of weird. Somewhere in between, like a borrow type that you use when constructing your functions. So borrow types are references to existing objects. They lack ownership. They're usually short-lived. They generally can do without an assignment operator. Ooh, this is where it gets interesting, because it ties to defining equality. They can generally appear in arguments. Okay, unsafe to store them. It's basically the same kinds of gotchas that we have for references, but now they're sneaked into this thing that looks more decent or less scary, but it's just as scary as references, right? The interesting bits that are relevant to our equality discussion and type regularity is that string view is assignable. Assignment has shallow semantics because the underlying strings are immutable, right? Meanwhile, comparison has deep semantics because it actually does a lexicographic compare. So this is what you would expect. You would expect to compare the underlying strings, not some pointers, right? When the underlying data type is extant and it's constant, like it is for string view, we can sort of squint and say this type sort of behaves as if it's regular, although it doesn't satisfy all the requirements of a regular type strictly. But it sort of looks regular. So if we're using it properly in function arguments, because we have no surprises with the underlying buffer, because it's a constant thing that we're pointing to, we're not expected to modify things, we cannot modify it through the string view and so on. It sort of behaves as a regular type. But then we have this. And this one is really weird, because it sort of looks like string view, but the underlying buffer is no longer constant, and we're not expected to be constant. We're trying to do something to it. That's why we're using that span. We're not just reading it. So I'm going to skip the rationale. I expect people know. So what would Stepanov do? So turns out with span, we actually almost screw it up when we standardize it. Very late in the process, we actually sort of fix it. So the question is, should span be regular? And by the way, that's the paper that dealt with all the nasty details. Obvious things. Okay, the meaning of copy construction and copy assignment is to copy the value of the object. Okay, we've covered this already. Copy assignment and equality should go together. Okay, when designing, try to be regular. Okay, that's the manifesto. That's what we're trying to achieve when we design span, right? Make it, all these things say, make it regular, right? But what does really happen? So assignment is shallow. So it just does pointer and size. That's what all we copy, because span is meant to be cheap to pass around, so it is shallow. That's part of its design. We could make equality deep and maybe compare elements as if we're using standard equal on them, just like we do with string view, right? This is what string view does. So again, the intuition of the programmer is, okay, I know string view, I've been using string view, I get how it works, I'm using span now. Okay, I think it works the same. So these first two bullet points just say, span behaves like string view. However, string view can't modify the elements it points to, right? We've said that already. So a shallow copy of string view is similar to a copy and write optimization. That's just a consequence. But is span really a value? Can we consider span a value? Or is it just convenience structure that we manipulate memory with and traverse memory and refer to memory? Can we say if it's a value or not? Conceptually, I mean. And if so, do we need to do a deep compare? So span sort of tries to act like a collection. So it sort of tries to act like a vector. We can even construct easily stuff from collections. So it sort of tries to behave as if it's a collection. It has similarly named functions, and it's sort of almost there. But it's not a collection. Not really. It's not a collection. And it's definitely not regular according to any of the semantics that we defined for what regular means. More than this, I would say span has reference semantics, and arguably maybe it should have gotten a more explicit name like span ref or span PTR or something, I don't know. I guess span is more appealing as a name. So getting back to equality. So equality implies deep const, logical const, as extending to all its parts as per the definition in elements of programming. So we expect if we define equality to mean deep const, because it would be very surprising if we define it any other way. So all parts, all the things that constitute part of the value should participate in the equality operator, right? Right. Equality operator should do the same things that we do when we copy things, right? When you copy things, we copy stuff, right? And we expect to compare that stuff to say, okay, what we copied, we got the same thing, right? According to whatever whatever equality means for that thing. But again, span is not really a value. So deep equality means the value of the span and elements it spans, not just pointer and length. That's what deep means, right? So if we want span to act like a lightweight representation of its elements, we need to have like a shallow equality, just like we do for smart pointers, by the way. That's what smart pointers do. So shallow const means shallow equality. But shallow equality might be really confusing, especially like if you're trying to meet what you know. Like, okay, I know how string view works, and I expect span to work the same way. So it's sort of, I don't know, a bit surprising. So finally, what we got was a compromise thing. So, and the compromise was to remove equality altogether. And because we just couldn't figure out a way that makes sense and it just works. So I think it was the right thing to do, to remove the operator altogether. But definitely it's a strange thing, and it's definitely no longer regular, right? That's what regular means. Regular means equality comparable. So it's sort of not a value, not a container. It's a strange beast. So it's semi-regular at best. I chuckled when I saw this picture from Corentin a few years back. And by the way, if you want to like really gnarly details about span, do read this article. It's very good. So for non-owning reference types like string view and span, you need more contextual information working with them to understand these concepts: shallow, compare, mutability, how we define equality, and so on. So it's a lot of work. So I would say it also has some implications when dealing with these types. So I would say my call to action would be make your types regular when you can. Model them as closely as what you have in the standard library, not span, right? Think of strings, think of standard vectors, think of integers. So that's what you should try to aim for. So sometimes, yes, we need to define utility stuff like string view and span because they're just convenient. But I would say those should be the exception rather than the rule. Okay, I don't have time for question on record, but the program is over, so we have plenty of time to chat in the hallways or over drinks. Thanks.